Okay, so our lesson today is lesson 1.3, and we're talking about solving equations that have variables on both sides of the equal sign. So that's the next step that we're dealing with today. Everything that we've done, even the multi-step equations that we did yesterday, even, if they weren't simplified, the variables were all on one side of the equal sign, either on the left side or on the right side, but not on both sides. So the variables were contained on just one of the expressions. Today we're going to review how to handle it if both expressions on either side of the equal sign have a variable on both sides. So there you go. So we have a step-by-step here, and we're just going to go through it and then just summarize it. Essentially, we're building. It's like layers. So we talked about in class, you're building a layer on top of each of the previous lessons when we're talking about these solving equations. So when we're solving an equation that has variables on both sides, we're still going to make sure that we simplify either one or both sides of the equation. So we're still going to start off by looking at each side and making sure that it is as simple as possible. So that's still going to be step one, just like it was yesterday. We're looking if there's grouping symbols, if there's like terms. We're going to want to just pause on the whole solving thing and clean that up and make sure that it's fully simplified. Do the same on the other side. Make sure that there's no grouping symbols, that there is no like terms, okay, before we then proceed to the next step, okay? So when we talk about what would be step one when we're doing this is simplify one or both sides as necessary. Make sure that both sides of the equal sign are completely simplified. Okay, the new step is the second step. Actually, it's kind of wedged in between what we've been doing yesterday and the days before. So yesterday we simplified and then we solved. Okay, here we're going to kind of wedge a second step in the middle there. So after step one, where we simplify one or both sides, okay, step two is to use inverse operations to collect the variable terms on one side only. So that's our step two this time around. So we're looking at this being our step two, okay? And the idea here is once both sides are simplified, we're going to pick one side, and it actually doesn't matter a whole lot, but we'll talk about that further, and move the variables all to one side. So use inverse operations to gather all the variables so that they're on one side only. And then at that point, we'll proceed to step three, which is isolating the variable the way that we have been. Okay? So remember, if I'm writing it down, you're writing it down. To summarize that and just put it together, in a way that we can look at it, visit it quickly. Step one, simplify both sides completely. And then step two, gather variable terms on one side. And that's really the new step today. Okay, so this is the step that we are introducing today with variables on both sides. So we gather them all on one side, then we go back to business as usual, and we solve as our third step. Okay, so let's go ahead and get started. Number one, step one, simplify both sides completely if not already. So the first thing I'm going to check is separately, we're going to look at each expression. 12 minus 3x, and I'm going to just make sure that that's fully simplified, that I don't have any parentheses or grouping symbols, that I don't have any like terms. But in this case, I don't. I'm good to go. That's a constant. That's a variable. There's nothing I can clean up or do here. We're okay. Then I'll check the same thing on this side, and it's just a negative 6x. There's no parentheses. There's no like terms, so we're okay. But I always want to start with that step first and make sure I've taken care of that. Okay? However, when we move on, we do have this new challenge here that means that we have variables on both sides of the equal sign. So that's my goal, is to try to fix that. This is where we're going to use inverse operations, right, to gather the variables on one side only. So after I've simplified, I'm going to pick one of my two variables. In this case, I'm going to do the 3x, the negative 3x, and I'm going to use an inverse operation. Opposite of a negative 3x is a positive 3x, and I'm going to do that on both sides of the equal sign. Okay, now notice, normally what we were doing before is if I saw multiplication, I'd be dividing. Well, that's if I want to separate the 3. That's if, if I were trying to get rid of the 3 but keep x, I would do the opposite of that multiplication, which would be division. But in this particular scenario, I'm not trying to keep the x. I actually want the entire term disappearing from the left side because I want all my x's in one place only. So when we are gathering the variable terms, we are literally always just going to look at that opposite sign and not just eliminate the 3, but eliminate the entire term. Okay? And then that leaves me with just 12. And on the right side, I have like terms. That's the whole idea. These are both x terms. And I can go ahead and combine those. So a negative 6 and a positive 3 is a negative 3x. And that took care of the problem of having x's on both sides. The x's are now in one location only, and I have, once again, a pretty simple equation, and I'm ready to solve now. Okay, last thing I need to do is now definitely separate the negative 3. See, do you see where our goal is different here? Here, our goal was to completely annihilate, make the entire term disappear, 3 and x, all of it. So I did the opposite sign. In this step, in this second level, I want to just get rid of the negative 3, but I want to keep x. That's the whole point. I'm trying to get x alone now, right? So I'm going to divide by negative 3 because that gets rid of the coefficient, right? Negative 3 over negative 3 is just 1, so that's just 1x, but it lets me keep the variable, okay? So let's figure this out. 12 divided by negative 3 is negative 4. And on the other side, the 3's canceled, but the x is still there. And so there's our solution. Our solution is x is equal to negative 4. So you can see how, depending on what your end goal is, that's going to determine what inverse operation you do. If I want the entire term to disappear, I'm going to do the opposite sign. If I want to separate that coefficient from its variable, then I'll use that multiplication or division. Okay, let's go to number 2. Okay, check to make sure both sides are simplified. 3k plus 45, that's okay. I don't have a grouping symbol or like terms. 8k plus 25, we're okay there. So we're all right on step 1. Step 2, gather the variables on one side. I do have this predicament of having variables on both sides. So I am going to pick one of those terms and do the exact opposite sign. So I'm using that inverse operation. And I'm going to do it on both sides of the equal sign. And I'm lining it up with the like term because that's exactly where I'm going to want to combine it. 3k's minus 3k's makes that whole thing disappear. So I have no k term on the left side anymore. Okay. That leaves us with 45. And then on the right side, 8k's minus 3k's, well, those are like terms. I can combine them. Gives us 5k. And I still have the 25. Okay. And then as we continue here, we'll finish this off by solving for k. So now that we have the k's in only one location, step 2 is done, right? I've gathered all my variables so they're in one location only, and all I have to do is chip away and do the inverse of the stuff around it and get that k by itself. So we'll start off by subtracting the 25 from both sides. And that cancels, and I'm going to come over here to the side. 45 minus 25 is 20 is equal to 5k. And then in step 2, we'll divide by the 5. That allows us to cancel the 5 but keep the k. And so 20 divided by 5 is 4. So in this case, a is equal to positive 4. There's our solution. You could always plug it in and check to see that it works. But I'm pretty confident we're good on that one. Okay, let's go on to number 3. So on number 3 here, if you look at the problem, when we check on step 1, the left side looks good, 5q plus 6, nothing I can do there, that's simplified. When I look on the left, whoa, yeah. On the left here, I have a couple of like terms that you're going to be expected to be able to kind of see and combine. So step 1 is going to be in effect here. I have 2 q's plus another q, so I can rewrite that much more easily as 3 q's. So I can write it like that. Okay, so 2 q's plus 1 q is 3 q's. So combine like terms. So that was step 1, which is simplify completely. Okay, now let's gather our variables, because I do have q's here and here. So gather the variables on one side. Back to the conversation, it doesn't really matter. I have 2 options here. I could subtract 5q and cancel this one and get the q's over there. Or I could subtract 3q and cancel that one and get the q's over here. What you're going to notice that I do is that I try to move it, most of the time I try to move it so that things stay positive. I'm a positive kind of person. And even though I can handle negatives really well, if I can avoid them, I still like to avoid them, right? They're just a little Pandora's box of small little careless errors that if I can avoid, I'd rather do that. So like on this example, I think I'd rather get rid of the 3q's by doing minus 3q and letting the one on this side on the right cancel and ending up with a positive here. 5q's minus 3q's is 2q equals 6, and on the other side it's negative 2. Okay? All right. And then we have just the q's in exactly one location. And we can now just go to step 3, which is do the inverse here and solve. So negative 6 and negative 2 is a negative 8. And then if we divide both sides by 2, we get that q is negative 4. Lots of 4 answers here. That's a coincidence. That's not always like that. Okay, going on to the next one. Definitely some simplifying that can be done here on number 4. We have to make sure we distribute. We don't want to leave grouping symbols, so that's step 1. We're going to simplify both sides. So in this case, that means we're going to distribute. 2 times 4b is 8b. 2 times negative 6 is negative 12. On the other side, 4 times 3 is 12b. And 4 times a negative 7 is a negative 28. And then step 2, gather the variables on one side. So I can move either the cancel the 8s or cancel the 12s. I like to keep things positive, so I'm going to go with this guy. I'm going to cancel these. That'll leave me with that negative 12 on the left, and here it'll be 4b with the negative 28. Okay? And then now we just have a 2-step equation, and we go into step 3, which is just doing the inverse operations to solve. So we'll start by eliminating the 28, add 28 on both sides. I should say positive 28, not add. Positive 28 on both sides, these signs are different, so I'm actually finding that difference, and it is a positive 16 equals 4b, and then when we divide, oh my goodness, is this another 4? It is. Okay, again, totally coincidence. B is equal to 4. So many answers that are 4s. Okay, let's try number 5. This is when it starts to get fun. Okay, definitely grouping symbols, like terms, we've got it all on number 5. But again, if you just, if you take small little bites and just break it down step by step, it doesn't have to be overwhelming in any way. It might look a little intimidating, but if you follow the recipe, you're going to bake that cake perfectly every time, y'all. Okay, so step 1, simplify. And for us, that means distribute to get rid of grouping symbols and combine like terms. So let's do that. The 3x is not invited to that party, so we're just distributing the negative 8. So negative 8 times 2 is negative 16x, and negative 8 times 3 is a negative 24. Okay, and then I notice I do have a couple of like terms right here that I can combine. So positive 3 and a negative 16, that's a negative 13x. Like that. All right, and that's as much damage as I can do on the left side. Let's do the distribution on the right. If I distribute the negative 6, I get negative 6 times 2x is negative 12x, and negative 6 times 5 is a negative 30. And that's as simplified as we can get it. Now we go to step 2, gather our variables. So I'm going to go ahead and move the 13, do the inverse operation, completely eliminate them on the left side. And then that leaves me a negative 24. On the right side, negative 12x, and a positive 13 is just 1x. And that's with the negative 30. So now coming up here, I've got negative 24 equals x minus 30. And how nice is that? Just a one-step, what looked pretty intimidating became just a one-step equation. I'm in step 3 now, and all I have to do is eliminate the 30, and we're done solving. So if I eliminate that, I get that x must be the difference between negative 24 and 30, which is 6. Yay, it's not a 4. Okay, so it's x equals 6. There you go. All right, moving on. You guys are getting the hang of it. I'm going to go through a little bit. This side is simplified. This side we're distributing the 8. So this is going to stay exactly the same. On the right side, I'm going to distribute that 8. Get 16f and get 24. Okay, and things start to get pretty interesting here. I want you to see what happens in this particular problem. You might already start to see it here ahead of time, but once I distributed, I got 16f, and now my second step, right, because I'm done simplifying here and here, would be to gather my variables on one side, because I have f terms here and f terms there. So when I go to say, okay, well, let's cancel this one, let's say, and we do a negative 16f. And then I do this side, and it's a negative 16f also, though. And it's like, wait a minute. In my effort to try to cancel it on the right, on the left, it automatically also cancels on the right because they're identical. So now I don't have any variables. Unlike over here, you know, where they were different, and so when I try to get rid of one, you know, it just moved, and then I still had variables on the right side. Here, when I try to cancel one, it cancels both because they're identical. I can't get rid of one without getting rid of the other. Well, that's actually not the end of the world. It is something that happens mathematically, and it has some mathematical importance, actually. So here's the deal. When that happens, as long as you check your work and you know you've done it correctly, then you can be, you know, rest assured that it's not a mistake on your part, that this is what we call a special case. It's a special type of equation. Okay. What really matters, though, is to see what's left. So when these f's cancel, okay, what am I left with on the left side? Well, I'm left with a 24. What am I left with? And then there's an equal sign in the middle. And then what am I left with on the right side? Well, it's also a 24. Here is where truly the answer is going to reveal itself, okay? If the variables cancel on both sides, it's a special case. What kind of case is it? Well, this is going to tell you. This is not our answer, so be careful not to box this. But it's going to reveal to us what the answer is. So when I see 24 equals 24, I ask myself, is that true? Is that a true statement? Is 24 equal to 24? And if the answer is yes, then that means that this has all real solutions, or all real number solutions, right? So all real number solutions. Okay, and what that means is that this is a special scenario where there's not one unique answer, only one number that works or makes it true. Any number I plug in for f makes this true. This side is equal to this side no matter what value I give to f. F could be 0, it could be -5, it could be 10, it could be 1100 million. It doesn't matter. If I plug it in here and here, this side still equals that side because the two sides are essentially identical. Okay, so this is an equation that has infinitely many solutions. Okay, so you could say that the solution is all real numbers. You could say that it has infinitely many solutions, but that is the answer, and that is what I will be looking for. That is not an answer. 24 equals 24 is not a solution. Saying that it is true is not a solution, but it does inform us that the solution is all real numbers, or that there's infinitely many solutions. So you could say all real numbers, or, you know, infinitely many solutions. If I can, Yep. And both of those are acceptable. Both of those are truly answering the question of what makes this equation true. That is not answering that question, so just be careful with that. This is what I'll be looking for, okay? All right, let's try the next one here. Oh, let me back up. Let me actually just talk about this, to finalize this idea. There's one other special case. If this had happened, for just a moment, let's just talk about theoretical. Let's pretend this had been, I don't know, an 8 right here instead, right? And everything else was the same. So I get 16f plus 8, I distribute, the 16s cancel, but then I end up with a statement that says 8 equals 24. Well, that's not true at all. That's nonsense, right? So 8 does not equal 24. That doesn't even make mathematical sense. When that happens, that's the other type of special case that we call contradiction, and it has no real solutions. So it basically means that no matter what you plug in, this side will never equal that side. Okay, so if we had been able to cancel out both sides of the variable, but gotten a statement where one side is not equal to the other, and my variables are gone, and I have something crazy like 5 equals 7 or 2 equals 9, and we know that just doesn't make any sense, that's no solution. Okay, so there's two special cases. There's the identities, is this guy that has all real numbers are solutions, and then there is contradictions that have no real solutions. They have no solutions. Okay, all right, now that I've said that, let's continue. Okay. Now these get fun and interesting because I want you to notice that there are multiple variables here. So there's x's, and then right in here there's that r that they're wanting us to solve for. So this is kind of like the literal equations lesson, coming into play. So let's take a look. We have, let me make sure we're on the, yeah, actually, we are going to skip this because we're going to actually do a whole lesson on this next time. So don't worry about 7 and 8. Okay, let's just scoot over. You're not going to have any problems like that on your assignment. And we're actually going to spend a whole lesson talking about this literal equations coming up. So let's solidify our conversation about what we talked about, those special cases. Special solutions, right? So equations that don't always have one solution. An equation that is true for all values is what we call an identity. And those guys have, like I said, infinitely, let's write that word out. It's our notes, we should do it right? So infinitely many solutions. Those are the identities. And then an equation that is not true for any value at all has no solutions. Okay, those are the ones that we call contradictions. Okay, so let's explore that just a little bit more and see what that looks like. And sometimes they do still have, one solution, and that's fine. So let's try this one. Simplified, we're okay with that. Step 2 is gather your variables. So I'm going to move the 5y, cancel it on the right, and make sure I only have y's on the left side here. And as soon as I do that, if these are not at a perfect match, and I was able to cancel them on the right and still have some y's over here, then I know that this is not one of those special cases. This is going to be a normal problem that just has a solution, and that's okay. Most of the problems will be like that. So now that I have this, I'll solve for y. That's step 3. So I will get rid of the 13 with a negative 13. So that's 2y equals, well, negative 16. And then we'll divide both sides by 2. So here, this has a solution, one solution, and it is negative 8. So in our directions, it is said determine whether the equation has one solution, no solution, or infinitely many. And if the equation is neither, then find the solution, right? So, well, not if it's neither, but if it has one. So this has one solution. And that solution is y equals negative 8. That is the one solution that makes that statement true. So we're okay. Let me make sure. Yeah, that looks good. Now let's try this one. I check to make sure both sides are simplified, and they are. I gather my variables. Right away I start to see that those variables are a match, so as I try to eliminate one, I will inevitably cancel both. I can't cancel one without canceling the other because they're identical. This is where I know it's going to be one of these special cases. Okay, so as I try to move one over, or cancel one, I mean, and move it over, yeah, it's going to just cancel it on both sides. And now I know that that's okay. The world is not going to end. But what's really important to determine if it has infinitely many solutions or if it has no solutions is what is left behind. When these p-values are canceled, what am I left with on the left side? Well, it's an 8. An equal sign in the middle, and what's left over here? A -7. And I want to ask myself, 8 equals -7. Does that make any sense whatsoever? And probably the answer is no, that does not make sense. And so we're going to not, put on here that say this has no solution. This is one of those contradictions where it doesn't matter. You could spend the rest of your life plugging in numbers here and here, and you're not going to get anything that makes this true, and it works. Okay? So that one was pretty obvious because right away we could see they are a match. The trick is that sometimes we don't see that they're a match, especially if the sides are not fully simplified. So that's another nice advantage to making sure that both sides are simplified. It's just to look at this and decide, oh, okay, this is definitely... this is definitely one of those special cases. So here it might not jump out at me that I have a special case, but as I start to distribute and simplify, 3 times 7, I know is 21R. And 3 times -2 is a -6. Now that I see this simplified, I might start to pick up on the fact that I have a special case, that once I simplify it, I actually have two identical R terms. And in fact, the whole expression is identical. And when the whole expression is identical, then that's how I know this is going to be, infinitely many solutions. As I try to eliminate one, it's going to eliminate both. And I'm going to be left with a statement that is perfectly true. So as I try to cancel one, it'll cancel both, and I'm left with -6 equals -6, which is totally true and makes very good sense. So then I know that this has infinitely many solutions. Many solutions. So don't just assume until you have fully simplified, right? Same thing on this one. They might not look exactly the same, but as I distribute here, 2 times 3x is 6x, and then 2 times 6 is 12. And on this side, 3 times 2 is 6x, and 3 times a -6 is a -18. And I can start to see that these guys are a match, and these are not. So I can see, okay, these are a match after I've simplified. I can see I have the same x terms. I'm pretty much going to have a special case. Which kind of special case is it? Well, let's see. When I try to cancel one, it cancels both. But this time I have 12 on one side and a -18 on the other. Does 12 equal -18? Nope, not the last time I checked. So this is no solution. And that's your answer. Not -6 equals -6 or 12 equals -18. This is your solution. That's your answer. That's your answer. All right, let's try the next one. Let's do a little bit of a word problem here. This is all about the value of the surface area of a rectangular prism has, let's see, the value of a rectangle is equal to the value of the volume of the rectangular prism. So write and solve an equation to find the value of x. So here's our figure. This is the formula for volume. This is the formula for surface area. And we're basically saying that the two, for this particular one, the two are equal. So the volume formula for this particular shape is length times width times height. And then we're saying that that's equal to the surface area which is base times height. Oh, sorry, I wrote those, yeah, volume. Sorry. Perimeter times height plus 2b, okay? So that's equal to that. And then we fill in what we know. So let's start with the volume. So the volume is the length times the width times the height. So it's basically the product of these three things. So it's that x times 6 times 6. Okay, which simplifies to 36 there. Okay, on the other side, we're going to do the perimeter across the bottom. So let's talk about what that looks like. Well, perimeter is usually 2 times the sum of the two sides. So it's x plus 6 here times 2. That's our perimeter. And then we'll multiply that by the height, which is also 6, plus 2 area bases. Well, the base is length times width, so 6x. So 2 times the area. So down here, the area would just be the length of those multiplied together. So 6 times x. Okay? All right. And then we clean all that up, of course. We'll clean that up. We'll distribute the 2 here. And that's times 6. Here we can also add that together. We get 12x. We'll distribute 6 this time. So 6 times 2. And 6 times 12. That's what? 72. Plus the 12x. And then we'll combine this x term and that x term. So we're going to do one more line here. And I get 24x when I combine those. Plus the 72, that is a constant. Woo! All right, so now that we've used our formulas, we know that the value of the volume is equal to the value of the surface area. They're both simplified. Okay, I've simplified both sides. Now let's gather our variables. I like to keep things positive, so I'm going to cancel the negative 24 and move it over to this side. And that leaves me with 12x equals the 72. And then we'll just divide both sides by 2. So I'll come over here. And if I divide both sides by 12, I think I said 2, but it's 12. And then I get that it is 6. So the length of x is 6 units. That it would have to equal x would have to be 6 if the volume ends up being equivalent to the surface area. Okay? Okay. And then last but not least, let's see. 1 serving of oatmeal provides 16% of the dietary fiber that you need daily. You must get the remaining 21 grams of dietary fiber from other sources. So how many grams of dietary fiber do you need every day? So let's see. We've got, you must get the remaining 21. Okay, so 21, let's see, 16% of what you need. So whatever it is that you need, let's call that x. Let's call that, if I do this percentage, and I have to move the decimal over twice, times what I need, okay, that equals 1 serving. Okay, so that's 1 serving. Okay, the remaining 21 grams you have to get somewhere else. Oh, so let's think about this in a better way, actually, now that I rethink this. So if that 1 serving is 16% of what you need, then the remaining 21 grams must be the other 84%. That's a nicer way to write this. Okay, so if 16% represents what you've already had, let's say, of 1 serving, and the rest that you need is 21, then that means that the other 84% of the daily need has to equal that 21 grams. There it is. And if we set it up that way, that's actually a nice, simple one-step equation. And then all we have to do is divide both sides by that decimal. And we get that x is equal to whatever that lovely number is. So let's go off to the side and divide that. I'm going to move the decimal over. We've been reviewing this. Now if I have to move the decimal over twice to get a whole number, I'll have to move that decimal. So I'm really dividing 2100 by 84. And I'm going to go on a limb and say that goes in there twice. It does not go into 2. It does not go into 21, but it goes into 210. So, and I'm going to say it goes in twice because I know that's going to be 8 and that's 16. Okay, and then let's see what's this difference. Let's borrow. That's a 2, and then I'll borrow again. That's a 42. Okay, and then I bring this down and I try again. I think I'm going to go for maybe 5 here. Let's try that. 5 times 4 is 0. Carry the 2. This is 40 plus 2 is 42. And awesome. It worked out perfectly. No remainder. So your daily need is 25 grams. You need 25 grams daily to get your full dietary fiber needs met. There it is. So we'll say you need 25 grams daily. Excellent.